On the last video, we reviewed the basic structure necessary for a proper system to define probabilities. Let's remember that we construct a probability space with three mathematical objects: the sample space, the sigma algebra, and the probability function. Before diving into unknown territory, let's take a minute to analyze and understand intuitively the necessary conditions imposed for a valid sigma algebra and probability function. We'll recall that a set F is called a sigma algebra of omega if it satisfies the following. Number 1, omega is an element of F. Number 2, F is closed under complements. And number 3, F is closed under countable unions. Considering our original dice roll experiment, we can find the events of rolling any number between 1 and 6. However, let's not forget that we could also observe other events such as rolling a number greater than 4 or rolling an even number. First, since rolling a number between 1 and 6 is an event itself, then clearly omega has to be an element of the sigma algebra, which corresponds to property number 1. Now, if we can calculate the probability of rolling a 1, we wish to be able to calculate the probability of not rolling a 1. In other words, if A is an element of the event space, then its complement must also be an element of the event space, which induces property number 2. Finally, if we consider a sequence of events, like rolling either 1, 2, or 3, it's desirable to calculate the probability of any of these happening. This means the union of all these events should be an event itself, resulting in condition number 3. A similar analysis can be done over the conditions for the probability function. Number 1, for any event A, the probability of A is between 0 and 1. Number 2, the probability of omega is 1. And number 3, if A1, A2, and so on is a sequence of mutually exclusive events, then the probability of the countable union equals the sum of the probabilities of each event. For those unfamiliar with more technical math vocabulary, the sets A and B are said to be mutually exclusive if they don't have elements in common. Another way to represent this property in mathematical terms is to simply state that the intersection of A and B is equal to the empty set. In this case, conditions 1 and 2 come naturally from our own understanding of probabilities. By definition, all probabilities are between 0 and 1, which translates into condition number 1. Moreover, we define the probability of inevitable events as 1. Since rolling a dice surely results in a number between 1 and 6, the probability of omega has to be equal to 1, yielding condition number 2. Lastly, given a sequence of mutually exclusive events, it's logical to define the probability of the union as the sum of the probabilities of each event separately. Think about rolling a number 1, 2, or 3. If we consider each event separately, their probabilities add up to 1/2, which is expected since 1, 2, and 3 represent half of all possible outcomes. This results in the third and last condition for our probability function. Now, like I mentioned in my last video, we can derive a few immediate results from these assumptions. Personally, I believe that math, if not visualized properly, just becomes a bunch of abstract statements with no meaning at all. So, for the sake of developing a true mathematician's intuition, let us give a simple proof for some useful properties of the probability function. First off, we mentioned before that the probability of the union of two events A and B equals the sum of each probability minus that of the intersection. A way to picture this statement is by breaking the union of A and B into three distinct mutually exclusive events. On one hand, we have the event A, which includes the intersection between A and B, and on the other hand, we have the elements in B that are not in A, namely the intersection of not A and B. Since these two sets are mutually exclusive, meaning there is no intersection between them, we know from property 3 of probability functions that the probability of the union is the sum of each probability. Now, notice how the event B is simply the union of the purple and blue sets. This means we can actually recover the probability of B as the sum of the probabilities of both sets. And from here, we're led to this new equality for the intersection of not A and B. By substituting on our original expression, we conclude that the probability of A or B is equal to the probabilities of A plus B minus the probability of the intersection. I encourage you to try and come up with a similar argument to prove that the probability of not A equals 1 minus the probability of A. For this, you'll make use of conditions 2 and 3 of probability functions. Once we've better understood the structure and properties of the probability space, let's look into how the probability function is defined in different cases. Resuming our dice roll experiment, we first need to define the probability of rolling each face. In practice, we expect each face to have equal probability. However, this does not have to be the case always, since we could be working with a weighted dice. What's important here is understanding that we calculate probabilities based entirely on the random variables defined. But what does that mean exactly? You might recall from the last video that we set our random variable x as the outcome of the roll. Though this is a very natural random variable given the nature of the experiment, there are other variables we could have come up with. For instance, we could define y as 1 if the outcome is even and 0 if it's odd. Notice how, even when working over the same framework of rolling a dice, both random variables have different properties and behavior. Under the assumption of rolling a fair dice, the probability of x being equal to any integer 1 through 6 is 1 over 6, while for y, the probability of it being equal to either 0 or 1 is 1/2. Furthermore, both variables induce completely different sample spaces. For x, we have the set of integers 1 through 6. We'll name it omega x. Conversely, the sample space of y, which we'll call omega y, is just the set containing 0 and 1. From here, we're in shape to introduce two of the most important concepts in probability theory. Let us denote a function p of x defined over all real numbers given by the probability of a random variable being equal to x. Since our random variable x only takes values over the integers 1 through 6, p of x is 0 for all x not in the sample space omega x, and is likewise discontinuous taking the value 1 over 6 in omega x. By plotting the graph of p, we can visually represent its behavior. In probability theory, p is called the probability mass function, and its defining properties are the following. Number 1, p of x is non-negative, it's always greater or equal to 0. And number 2, the sum of p of x over the set omega equals 1. Now, let us consider a different function denoted by a capital F, which will be given by the probability that a random variable x takes a value less or equal to small x. In this case, notice how f evaluated in all numbers below 1 is 0, since the smallest number we can observe in a dice roll is 1. Now, the first interesting case is when x equals 1. By definition, f of 1 is the probability of the variable being less or equal to 1. Notice how the event x is less or equal to 1 can be split into two disjoint events, namely x is strictly less than 1 or x is exactly equal to 1. So, given property number 3 of probability functions, we can rewrite as a probability of x being strictly less than 1 plus the probability of x being exactly 1. Since a dice roll can't be less than 1, the first probability equals 0. On the other hand, the probability of x taking the value 1 is 1 over 6. Following up with this analysis, we observe that x cannot be equal to any number in between 1 and 2, which means that f of x still equals 1 over 6 for all x in the open interval 1, 2. At x equals 2, we can again separate into mutually exclusive events. In this case, the only ones with non-zero probabilities are x equals 1 and x equals 2, both with probability 1 over 6. Altogether, f of 2 equals 2 over 6. Notice how it's only in the integers 1 through 6 where f has a discontinuity. And additionally, these discontinuities are characterized by being 1 over 6 units apart from each other. Lastly, for every number x greater than 6, the probability of our variable being less than x is 1, since the dice roll can only take values up to 6. This generates a function with the following properties. Number 1, the limit as x tends to negative infinity of f is 0. Number 2, the limit as x tends to positive infinity of f is 1. Number 3, f is a non-decreasing function. And number 4, f is right continuous. This is what mathematicians call the cumulative distribution function. I hope that it's clear how it is possible and also natural to apply the concepts of probability mass functions and distribution functions to any random variable we can come up with. For instance, in the case of our previously defined y variable, its mass function equals 1 over 2 in both 0 and 1, while taking the value 0 for the rest of the numbers. Likewise, its distribution function is 0 for all numbers below 0, equals 1/2 for all numbers between 0 and 1, and equals 1 for all numbers greater than 1. But what about a variable such as a random number between 0 and 1? Remember, in the last video we concluded that the probability of such a variable taking any number is 0, so it wouldn't really make sense to define a mass function. If we try to apply the same logic here, we would end up with a mass function that is just the constant 0, which serves no purpose in calculating probabilities. Is it possible to view at this problem differently and come up with a solution? Well, fortunately for us, the answer to this question is yes. To solve this issue, mathematicians found a very clever way to generalize the concepts of mass and distribution functions to more complex variables. For the sake of clarity, let us consider a different experiment. Instead of just picking a random number in an interval, imagine yourself throwing a dart at a one-dimensional segment. Your goal is to land as close to the red spot as possible. Assuming you have good aim, it'll be more likely that the dart lands close to the spot and less likely it lands farther away. Let's define a random variable x equal to the distance from the left extreme of the segment to the dart. First, we'll consider a sequence of functions f1, f2, and so on that satisfy a very specific condition. Each function will be defined piecewise over subintervals of the segment in the following fashion. For f1, the segment is divided into two subintervals. The function will be constant piecewise in such a way that the area over each interval corresponds to the probability of the dart landing inside. Since the red spot in this case is inside the first interval, that means it is more likely the dart will land here. f1 will look more or less like this. A quick but relevant reminder is that since the total probability has to be equal to 1, that means the areas of the rectangles formed must add up to 1 as well. Now, for f2, we'll divide into 4 subintervals, over which the function, again, takes constant values such that the area of the rectangles is the same as the probability of the dart landing inside. One more time, the area of all rectangles adds up to 1. Continuing this process indefinitely, we start to notice this sequence approaching a distinct limiting function. This is precisely the function we're interested in. We shall denote it with the letter f and call it the probability density function of the random variable. Those with sharp intuition might already see an interesting relation between the construction of the density function and the concept of integrals. Certainly, the integral is naturally linked to the area under the curve of a function. Notice we specifically constructed the sequence so that the area under each function matches the probability of landing in a specific region of the segment. Since all functions of the sequence possess this particular quality, the limiting function will follow the same rule. In other words, the probability of landing in any subinterval ab is given by the integral from a to b of the density function. An important observation arising from this fact is that the integral over the entire set of possible values has to be equal to 1. With this in mind, we can now properly define the notion of choosing a number uniformly on the interval 0, 1. We understand the idea of uniformity as having no preference over any section of the interval. This implies that any two subintervals of similar length will have the same probability of containing the value. If we divide the interval in subintervals of equal length, all must take the same value for them to have equal probability. This induces a density function that is constant over the entire interval. Moreover, given that the integral over the entire interval must be equal to 1, that means the constant must be 1 as well. So, the density function of a random variable that takes values uniformly over the interval 0, 1 is just the constant 1. And what about the distribution function? Well, in this case, it is possible to keep the same definition as before. By considering f of x equal to the probability that our variable is less or equal to x, we can see that this is the probability of the variable taking a value inside the interval -infinity to x. In other words, f of x just equals the integral from -infinity to x of the density function. This equality turns out to be extremely useful. For those who have taken a calculus course before, might recall a major result known as the fundamental theorem of calculus, which informally states that the integral is the opposite operator of the derivative. Since the distribution function turned out to be the integral of the density function, then this means the density function is the derivative of the distribution function. There is an important distinction from the example of the dice roll, and it's essential to differentiate between both cases. There are two fundamental types of random variables, discrete and continuous. Discrete random variables are those whose sample space is either finite or at most countable, like any set containing only integers or rational numbers. In contrast, continuous random variables are characterized by taking values in an uncountable set, like an integral. Let's remember, in the case of a dice roll, the power set of our sample space omega was a sigma algebra, where it was possible to correctly define probabilities, but it wasn't the case with a sample space as big as the interval 0, 1. We briefly mentioned the concept of Borel sigma algebras, but what are they exactly and what purpose do they serve? Even if these concepts don't apply just to the study of probability, it's important to understand their nature in order to correctly describe the behavior of certain phenomena. For the time being, these questions will be left unanswered for a future video. As always, I hope you found this video helpful and interesting. If there's something in particular you'd like me to cover, feel free to let me know in the comment section below. Without anything further, thanks so much for watching.